Welcome. Let me give you, hey Shelby. Let's see,
Looks like it's going to be a tough crowd today.
Oh yeah. I imagine a couple more people might join, but you never know. Let me get myself pinned. You're not the one being recorded, mostly. How's it going?
Could be better. We had a quiz due Sunday for stats. And I was like, oh yeah, like I can do this, no problem. It was a little bit of a problem.
Yeah, how much time did you have for it?
We had like 70 minutes. We had a long time, but I felt like it was really like pretty quick. Like it was only 15 questions and they were good questions too. Like it wasn't like some of them were true or false. So I finished in like 25 minutes, I think.
Okay.
But yeah, I don't know. We can't see the questions yet that like we missed or that we got correct. So I don't know.
Are there any questions you remember from the quiz that you might want to talk about?
Yeah, one second.
That applies to everyone. Both. God, Kiha, I feel like I'm butchering it every time I try and say it. But if either of you have questions as well, feel free to bring them up. Let's see here. I know there were a couple things people asked about.
Can we talk about permutations versus combinations?
Definitely. Yeah. So here's the
because like one of the questions she gave us is that on the exam, like it was like you choose 7 basketball players at random out of like, or choose 8 out of 27. And then it says, you want to choose the 8 tallest ones, but I couldn't figure out if that was a permutation, a combination, or if it was just asking for the probability.
Okay.
Because it said, what is the probability that you choose the 8 tallest?
Sure. Okay. So the question we usually try to ask ourselves, if we're trying to determine if we're using permutations or combinations, is if order matters. So if I'm trying to pick the 8 tallest basketball players, does it matter if I pick the tallest one first, the second tallest one second, the third, right? No, the order doesn't matter. So at least right off the bat, I think it's probably a permutation problem. I'm sorry, a combination problem, because the order doesn't matter. So, gosh, my pens are all getting to be trashed. Let's see here. So if I'm trying to find, so how many were there total? 11?
There were 27 total. Choose 8.
So, and there's 8.
R.
Want to choose the 8. For, again, you just entered, here's the attendance form as well. And yes, I see your question. We can talk about random variable mean and variance for sure. So the way I often think about the probability, so there's a couple ways you can think about this, I think. But the way that makes the most sense to me, so the probability of choosing the 8 tallest is the number of ways to pick the 8 tallest divided by the number of ways to pick 8 people. Right? That seems to make sense to me. So if we're not worrying about order, there's only one way to pick the 8 tallest people. You pick all 8 of the tallest people. The more interesting part of this question is how many ways can you pick 8 people in general out of 23? pretty sure it's 23 choose 8, which is sometimes written like that. Sometimes it's written like.
I think it's 27.
Oh, sorry.
It's okay. It doesn't really matter what number, but.
That is definitely one way we could imagine doing this problem, which, I mean, the number 27 choose 8 is not nice, right? But it's, right, 27 choose 8 is 27 factorial over 8 factorial times the difference, which is 19 factorial. Whatever that happens to be. I think there's another way you could do this. I don't think so. I guess the other way you could imagine this question is if you were thinking about order mattering, you could kind of say, well, if order matters, right, how many ways are there to pick the 8 tallest people, right? Well, we have to pick the 8 tallest. There's 8 of them. So for those 8 spots, how many choices are there for the first spot? Well, there's 8 choices. You can pick the tallest person, the second tallest, all the way to 8. And then for the second spot, there's 7, 6. Divided by, now, I feel like this is going to come out wrong, but we'll see. So for the, no, I think this is going to come out right. How many ways are there picking, right? So again, this is the things we want. And then we're going to divide by the number of ways of picking any 8. Well, again, if we're thinking order matters, which it really doesn't, but you can still kind of do it this way. There's 27 ways of picking the first person. Sorry, yeah, 27. And then 26 ways of picking the second, all the way down to 20, right? Now I have to write out. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And so the way I think about this number, 27 times 26 all the way down to 20, is it's really just 27 factorial over 19 factorial. Right? I want all the things multiplied by 27 and less than down to 20. So I take away all the ones that are 19. And if I do, if I do this divided by this, I'm exactly going to get that. I think. I hope. Oh, no, we get 1 over that, right? So, right. So let's just make sure. This divided by this. Is really 8 factorial times 19 factorial over 27 factorial, which is exactly 1 over that. Yeah, it works out. So that's how you would, those are the couple ways you could imagine both of these.
Okay, thank you.
And of course, there's the attendance again. Yeah, definitely. So I would say more generally, when you're talking about permutations versus combinations, is, well, again, it's an order matters thing, right? Permutations, I feel like, come up less in probability and statistics, but not never. It certainly can come up if you're like talking about, say, like, for example, so let's say there's a race and there's 10 people running the race. And we're going to say there's 2 different ways we can think about the question. How many different ways can we pick the top 3 finishers? Not caring about who's first, second, or third. So this is a question where order doesn't matter. We're saying how many different ways can there be a top 3? And that would be 10 choose 3. Right, there's Now, if you're actually trying to calculate this, you can definitely use a calculator, right? Most calculators have a button. I definitely found mine, right? I think I showed you guys before. Ooh. It's right there. It's that NCR one. And so I'm just going to do 10, and then I'm going to hit NCR, which I have to hit my button like 3 times to get there. And then 3, and you get 120. This one is small enough you could actually do the math. Right, 10 factorial divided by 7 factorial is 10 times 9 times 8. And then the 3 factorial is 3 times 2 times 1. And so, I don't know, cancel some stuff, cancel a 3 here and a 3 here, a 2 here and a 2 there. And you get 5 times 3 times 8, which is 15 times 8, which is 120. But I don't think you should do it by hand most of the time. So, for example, if you were asking, like, what's the probability that my 3 friends finish in the top 3, you'd say it's 1 out of 120. Like, there's one way your 3 friends can finish top 3 out of 120 different ways anyone can. On the other hand, you could also ask how many different ways can we award first, second, and third place. Well, here order matters, right? If you pick, I'll use my brother's names, James, Daniel, and Michael to be the top 3 finishers, there's 6 different ways they can have the top 2 places, right? Where 6 is 3 factorial, right? I can be first, my brother can be second, my brother can be third, or I can be first, and then my brothers can switch places, and there's all sorts of different things that happen. So in that case, right, here order matters. I feel like there's not a good notation for permutations, at least not that I'm aware of. So for permutations, we can write 10PR, right? Or 10P3 NPR, like the radio station. Right, that is what it says, right? Yeah, NPR. How funny. So that's just, it's the same as this, except you don't have the division by the 3 factorial here. So this one here, so I should say, right, 10, gosh, keep wanting to write something different. My brain won't let me. N, choose R, is N factorial over R factorial times N minus R factorial. Right here, you're basically, this part here, this is the total number of ways you can order them, and then dividing by R factorial discounts all the different permutations you have. Whereas here, we want all the permutations, so this is just going to be 10 factorial over 10 minus 3 factorial. Or more generally, NPR is N factorial over N minus R factorial. Really, I'm not even thinking of it that way. I'm just thinking of, well, let's see. There are 10 choices for first place. And then once I've chosen the first place person, there are 9 choices for second place. And then once I've chosen the second place person, there are 8 choices for third place. Which is exactly what this number is here. 10 factorial divided by 7 factorial, everything 7 or lower cancels out, and you get 10 times 9 times 8, which is just 720. Right, it's the 120 ways we could pick 3 people for the top, and then times 6 for the 6 different ways you can permute each of those 3 people picked in the top. So, yeah, those are some examples. Sorry, my hair got in the back. Oh, jeez. It's getting longer. Most people voted for letting my wife cut my hair, which I don't know about that, but we'll see. She did cut it one time, many years ago when we were first dating, but I had very cheap clippers and it definitely was painful. If we try this again, I will definitely buy some clippers that work better. I don't know though. All right, so let's see. I see, talk about random variable mean and variance. Okay, let me actually grab the OLI stuff here so I can look at it. So I actually did, I'm all caught up with the book. I've gone all the way to Unit 4 and looked at her stuff. So let me grab. Also, gosh, what am I looking at here? one sec. I'm not seeing what I want. I find this book, although I like the textbook, like I think the material is good, and I feel like they ask good questions as you're going along, and like filling out the little whatever, like the various multiple choice stuff, I think is very useful and helpful. I find it hard to navigate and find exactly what I'm looking for some of the time. Like, I know there's a whole thing about random variables in this textbook, but I'm not seeing it where I feel like it should be. Yeah. Oh well. So let me see. There was something that literally just crossed my mind, went in and out. For a sec. Where'd you go? Oh yeah. Okay. So random variables. I guess I need a little more direction. Not like what about the mean and variance? Like, are we talking Z-score kind of stuff? Are we going in a different direction? Okay, sure. All right. So, was it last class? I think it was last class. So I think on Thursday's class, which some of you might not have been in because it's mostly Nindari's class, we definitely did talk about Z-scores a lot. So not that we won't talk about it right now, but if you want more on Z-scores, we definitely did a lot of examples on Z-scores last Thursday class. So I encourage you to watch that if you have questions, because we did a lot of examples like I'm about to do right now. So I will try not to do the exact same examples because that would be lame to do these examples and then those. So let's make up some numbers. Let's say we are, what do I got? Let's see. Some sort of data that is, I try to pick things that are realistic. Let's see if I can make up something that seems reasonable. Let's talk about, sure, I'll use weight instead of height. Often I go with height. Height is easy. Let's talk about average weight for a man. Let's not talk about people. Let's talk about elephants. Why not? Sure. I have no idea what an elephant weighs. That's probably not the best idea. Whatever. What's an elephant weigh? Who knows? Let's find out, just for fun. And then we'll make it easy. Elephant weight. About 13. Oh, there's a big difference. You got Asian elephants, you got African elephants, African forest elephant. Let's go with the Asian elephant at approximately 8,800 pounds. So we'll say the mean is 8,800 pounds. And we will say the variance, I'm just going to make some shit up. Let's say the variance is, I don't know, let me think. Let's say 200 pounds. That seems plausible. It's probably bigger. I don't know. All right, so there are two types of questions we can usually ask about Z-scores. And those questions are kind of, what's the probability that someone has, or some elephant has a weight that's bigger than or less than some number? Or what weight would some elephant have to be heavier than some proportion of the population, or less heavy than some proportion of the population? So basically, it's I can give you the weight and we can find the proportion of the population, or the percentage, or I can give you the percentage and we can find the weight. Those are kind of the two styles of question. To me, for those of you that have ever learned about exponential growth and decay, it's kind of the same sort of thing as for exponential growth and decay. I can give you the amount of time it takes for something and ask how much stuff do we have left, or I can tell you how much stuff is left and we can ask what time is it when that happens. All right, so, and let me see, do you guys, has Whitener given you guys a specific Z table she wants you to use? Because I've looked at her, not yet, okay. All right, well, let me give you, so I've got one that I've been enjoying using, but I'll also talk about the one that's in the well, it's not in your guys' textbook, so I don't know. So assuming you can use whatever source you want, where is my Z table? Sorry, I put it, oh, there it is right there. Let's grab this. Sorry. So here is a Z table. I would encourage you to look at that one. And what this Z table gives you is it gives you all of the area to the left of the curve. So just for example, if I scroll down to the second page of it and look at, say, a Z-score of 0.84, I see, so if I look at 0. And I encourage you all to look along with me. If I look at 0.84, I see a value in the table of 0.79955. Most of the tables that are in books usually cut off at the fourth decimal. So I would round out to 0.7996. What that's telling me is it's telling me that all of this area to the left of the curve is 0.7996, or 79.96% of the area. So if you had an elephant with a Z-score of 0.84, then they would be heavier than 79.96% of all elephants, and they'd be less heavy than the complement, which would be 20.04% of all elephants. And in fact, we can answer that question. So let's in fact, here's a good. So here's how we could use this. But so I want to point out, not all Z tables give you all the area to the left. The one in the Namdari textbook, in fact, I can show it to you guys right here. The one in the Namdari textbook, if you want to look at this for a second, sorry, I actually have it, but it's just easier for me to hold it right now. If you look at this one here, if you look at this, sorry, this Z table only gives the area to the left of the curve down to the middle. So if I looked at 0.84 in this one, well, in fact, we can look here. If I look at 0.84, sorry, this is getting kind of dumb here. If I look at 0.84, you can see the value is, hopefully you can see, it's 0.2995 instead of 0.7995 or 6. They might have rounded the other way. And that's because they're only going down to, gosh, sorry, it's hard to get this here. They're only going down to 0, and then you would add on the other 0.5 that's all that over there. So Z tables are different depending on what source you are using. So for this one, I could ask the question, what weight would an elephant be if it was heavier than 80% of all elephants? And so I should probably actually look back at my Z table for just a second, because there are some minor rules about how you're actually supposed to do this. So if I look at my Z table, let me share my screen just in case you're not looking. The nice one about this one I found also is you can highlight things when you mouse over it. So if I look down here, if I look at I'm looking for 80% in the table. So I see I have 0.79955 here and 0.80234 here. And so what you're supposed to do, if you don't have an exact value, and most of them won't be exact, is you're supposed to split the difference. So you're supposed to say the Z-score here is actually 0.845. So I'm going to say my Z-score is 0.845. And then we're going to translate that Z-score into an actual X score or weight. And so as a reminder, what the Z-score means, the Z-score means I am that many standard deviations away from the mean. So I am positive 0.845 standard deviations above the mean. So here's how we calculate that. Come on. So typically we find the Z-score of something by taking the actual value X, subtracting the known mean, and dividing by the known population standard deviation. And this will tell you how many standard deviations you are away from the mean. So if you know the weight, you can calculate the z-score. If you know the z-score, you can calculate the weight. So in this example, we have 0.845, that's our z-score, equal to the unknown value x minus the mean, which is 8,800, divided by the standard deviation, which I think I said was 200. Let me double check on that. And so here's what I'm expecting to happen. I'm almost one whole standard deviation above the mean, meaning I should be getting a weight that's not quite, but close to about 9,000 pounds, because 9,000 pounds would be exactly one standard deviation above the mean, right? Because one standard deviation is 200 and 8,800 is the mean. So we're just going to calculate this. We're going to multiply by 200. That's equal to x minus 8,800. And then we're going to add 8,800. So x is going to equal this, which let's get out the calculator. 200 times 0.845 is 169. So I'm going to get 169 plus 8,800. That's going to be a weight of 8,969 pounds. So an elephant that weighed 8,969 pounds would be heavier than 80% of all the elephants of whatever type. I think African elephants. Again, I'll just remind you, totally made up the variance or the standard deviation. Didn't make up the average weight, but. So that's one type of question we can ask. The other type of question we can ask is, if an elephant weighs let's say 8,300 pounds, what percent of the population are they heavier than? And I will tell you, this question is much easier to answer with the z-table that we have online versus the z-table that was in the textbook there. So we're just trying to find the probability that x is less than 8,300. So we're really trying to find the probability that z is less than the corresponding z-score. So the corresponding z-score, we're going to do 8,300 minus 8,800 all over 200. So let's see, calculating that. 300 minus 800 is negative 500. Negative 500 divided by 200 is negative 5/2 or negative 2.5. So this question phrased differently is saying, what's the probability that we're 2.5 standard deviations below the mean? Because 8,300 is exactly 2.5 200s below that mean, which is 8,800. So then we look at the z-table. So I look at the z-table. I look for negative 2.5. So looking at my z-table, I go to negative 2.5, and I go over to just the very first spot where it's 0.00. So I get a value of 0.00621, or cutting it off with the fourth decimal, 0.0062. So not even 1%, 0.62% of elephants have a weight that is less than 8,300 pounds. So I want to say, if you're allowed to use any z-table you want, I would use this one. I feel like this one is the easiest to read. But let's ask a different question that makes it maybe a little bit more challenging. So we could ask a question like, what percent of elephants have a weight between, let's see, I don't know. Let's say 9,050 pounds and 8,800. Let's do 80. Sorry, I'm trying to make numbers that are slightly interesting. Let's say 8360. For some unknown reason, we really are interested in 8360 is lower than I think I want. I think I want 8560. Sure, that seems not wholly unreasonable. We were really interested in elephants to have these particular weights for some reason. Maybe we're trying to transport them and our car can only, I don't know. Who cares? All right. So we're trying to find the probability that our normally distributed random variable x is between 9,050 and 8,560. And for these ones, when it's a continuous random variable like this, you don't have to worry about if it's less than or less than or equal to, right? I think your textbook did briefly talk about how sometimes you do some little adjustment if it's discrete to continuous. I wouldn't worry too much about it. So again, we're going to change these both to z-scores. So really we're trying to find the probability that z is between, well, so the z-score here, 9,050 minus 8,800 divided by 200. That's, let's see, 250 over 200, which reduces to 1.25, I think. Yeah. And let's see, 8560 over, well, so 8560 minus 8,800 over 200. Let's see, it's negative 240 divided by 200, which is negative 24 over 20, which is negative 12 over 10, which is negative 1.2. So we're trying to find that. Now, if we look at both of these in the z table, here's what we're going to get. If I look at 1.25, and it's positive 1.25, let's see, looking at 1.25, I'm getting a value of 0.89435. So the value in the table is 0.89435. Now, we look at this value, negative 1.2, I get, so it's just the first column in the negative 1.2 row, I get 0.11507. What am I supposed to do with those numbers? Right? Well, here's the idea. Again, right, this negative 1.2 is all the area to the left there. And this positive 1.25 z-score, the value associated with it is all the area to the left there. So I want to find just this part here. I have to do the green area, which is this, minus the orange area, which is this. So I really want just the probability that z is less than 1.25 minus the probability that z is less than negative 1.2. Right, since my z table always gives me the less than values, I want to find the between. Say, oh, well, I want all of the less than this minus everywhere it's less than this, because I don't want it to be less than this. So that's going to be this number minus this number, 0.89435 minus 0.11507. And then, you know, get out your calculator and do some subtracting. And you get 0.77928. So about 78% of elephants have weights between those two weights. So are there more questions about z-scores, or should we move on to something else? You can definitely say more about z-scores if you guys want to talk more about z-scores.
I have a question about our quiz that you gave us.
Oh, sure.
So for the first question, for the first question, you only gave us the probability that it will bring relief given that it's a new headache drug, or the probability that it will bring relief given that it's a placebo. So how would we find the probability of R or the probability of P? Like just the probability of R or just a probability of P?
That is a great question. So this has to do with what's called the rule of, I think, the total probability rule.
Oh yeah, Bayes.
Someone asked me, someone mentioned, I think in one of the reflections, something about the 5 rules of probability, which I'm sure I know them in general, but I don't actually specifically know what that's referring to. So
I think that might be like the addition rule, the multiplication rule, Bayes rule.
Okay.
I don't know the other ones. So maybe the at least one. I don't know.
Maybe the complement rule, maybe independent.
The complement rule. The conditional probability. Okay.
Sure. Sorry, let me grab this quiz so I remember exactly what I'm doing here. Sure. Okay. So let me draw a picture because, well, not always, but a lot of times these kind of probability questions lend themselves well to a Venn diagram. So how am I going to do this here? Maybe we can cut this right down the middle. So here are the people that got the drug, and here, which I think I wrote as a D. No, I wrote as
it's an H.
An H. How did I pick H? Oh, a headache drug. That's why. Okay, I guess that makes some sense. Sure, why not? And here are the people that got the placebo. And then here are the people that had instant relief, right? So relief here, relief here. All right. So I'm trying to find the probability that someone had relief, right? So I'm trying to find the probability that someone had relief. Well, there's kind of 2 subsections of relief. There's.
Oh my gosh.
It's okay. This is a perfectly valid
question. Just read the question wrong. I thought you were asking like the probability of H, and I was like, I don't know how to find that.
Well, actually, so the probability of H is actually super dumb. So if you but it's kind of hidden in the question. So it says in a clinical trial, half the subjects are treated.
Oh my gosh.
So the probability of H actually we do need that. The probability of H. Yeah. So here's how I'm going to calculate this. The probability of R, oh my God, of relief is the probability that I have relief and I took the headache drug plus the probability that I had relief and took the placebo. Like those are the only ways I can have relief. It's either relief and headache drug or relief and placebo. If there's no other option. But then to calculate those things further, we have to use the way, so the way you calculate this intersection, you say, well, that's the probability that I was given the headache drug times the conditional probability that I had relief given that I was given the headache drug. Same deal here. This is the probability that I was given the placebo times the probability that I was having relief given that I was given the placebo.
Yeah.
Now, if these 2 events were independent, right? If relief and placebo or relief and headache drug were independent, these would just be P of H times P of R and P of P times P of R. Because when they're independent, that's how you calculate the intersection. These are definitely not independent, though. So we have to use this particular formula. And then, all right, so what's the probability that I was given the headache drug?
1/2.
Exactly.
2.5.
And then the conditional probability that I had relief given that I was given the headache drug is
0.9. Okay.
And then the probability I had relief given that I was given placebo is 20%.
0.2, yeah.
So that's how you calculate this.
Okay, got it. Thanks.
And then you'll use this calculation to answer the second part, right? So let me ask, what's the probability that you, and of course I was dumb and I changed my letter from H to D in the second part. Sorry about that. So maybe that should really say what's the probability of H given R. Yeah, I might need to fix that. Yeah. So the second person is asking what's the probability of H given R? And so you're going to use the conditional probability that's the probability of H and R divided by the probability of R. And then we already have those things, right? Here's the probability of R right here. And we also calculated the probability of H and R right there. So that's how you would calculate that's how you would use Bayes' formula to calculate the other direction. But yeah, I feel like I need to change that. So, or at least I'll send you, you know what, I probably too late to change it. I'll send you guys, everyone else, a message just so they know.
Okay, thank you.
Yeah. You guys have other questions? I can talk more about Z-scores, or I can talk about, oh, I know, someone else asked actually about, this actually pertains to the other quiz question. Someone asked something about like how the linear functions of a random variable work. I'm gonna use my elephant example again because I think this could actually work. So let's pretend like the weight of a baby elephant is a linear function of the weight of its mother that we'll also pretend has the same weight distribution as the father. Okay. So let's say, right, for our random variable x, that is the weight of I'll just change up the numbers a little bit, why not? The weight of a female elephant. I would assume they weigh less. I don't really know. Let's say that the mean is, let's say it's just 8,000 pounds to be nice and easy. And let's say the standard deviation is a little bit less. Let's say it's 150. Okay. It could be more. I don't know. So then let's say that y, which is the weight of their offspring, depends linearly on the weight of the mother. So the heavier the mother, the heavier the offspring. May or may not actually be true. So let's say it looks like this. Y is equal to, let's think here. Let's think what will make sense. Let's say it's like, I have no idea what a baby elephant weighs. I guess I need to learn that. Let's say it's 0.10 times x plus 200 pounds, maybe. Who knows? Probably seems a little heavy. Let's say it's 0.05 times x. So a baby elephant weighs 200 pounds plus 5% of whatever its mom weighed. I'm sure it's not accurate at all. So the question we want to answer here is, what is the average weight of a baby elephant? Okay, well, the way you do that is you just stick the average weight for x in for x. So the way they typically write this, so someone might write this as mu sub x, and this is sigma sub x to differentiate between the x variable and the y variable. So then mu sub y, the mean for the weight of the mean for the y random variable, would just be stick in the mean for x instead of x. This would be 0.05 times the mean for x plus 200. The mean for x was 800, so that's 0.05 times 800 plus 200. And 0.05 times 800, well, let's see, 5 times 8 is 40, so this is going to be 40? 400? It wouldn't be 400, right? Because 0.5 times 800 would be 400. So this is maybe my numbers are weird, whatever. This is 40 plus 200, which is 240. Probably on the light side for a baby elephant. Oh well. So that's the average weight. And then to find the average standard deviation, sorry, not the average, to find the standard deviation, we talk about average standard deviation. So define, so I will say for these ones, they typically talk about, instead of talking about the standard deviation, they usually talk about the variance. And it actually makes a lot of sense when we're talking about what's the other thing? When you're adding two variables together, the variance actually gets kind of weird. So let me see here. Gosh, I don't remember how it works. This is the one I always forget. I believe the way it's supposed to work is that the variance of the new variable, so sigma squared y, is equal to the coefficient 0.05 squared times the variance of the original variable. I should double check on that though. I definitely know I was reading this in the notes the other day. So 1 second here. It's impossible to find the things I want to find. I think it's, let me see, 1 second. Nope, that's not it. Oh, it's because there's like so I was looking at my OLI thing and I didn't realize you could scroll on top. I was like, this seems like they're missing like some of the units because I didn't see them. So there's permutations and combinations. There's random variables. All right. So mean and variance of a random variable. Yeah, sorry. It's probably this thing here. It's just never easy to find what I want to find. Sorry. Rules for mean and variance. Yeah, I think that's what it is. Okay, let's go back one. I think it's page like 159 or 158. Yeah, okay. So so we're right here. So the variance of the new variable is the coefficient of whatever your old variable was squared times the variance of the old variable. But if you're talking about standard deviation, you just square root everything and you get the standard deviation of the new variable is this multiplier times the old standard deviation. So here we're going to get sigma y equals 0.05 times 150, which is going to be 7.5. And where this is a little more interesting, which is not really in this example, but I'll just point out, is that when you have, so there's rules for a linear function of a random variable. There's also rules for adding random variables. So if you have like, so let's say, let's do this. So let's say X is the weight of a male. And again, we had said the mean of that was 8,800, and the standard deviation we had said was 200, I think. And then we have, let's use Z as the weight of a female elephant again. And we said the mean was 8,000, and the standard deviation was 150. We could ask things like, what's the mean of X plus Z? So what's the average weight of a male and female added together? Well, it's just going to be their averages added together. It's literally going to be, sorry, that should be a Z there. 8,800 plus 800, 8,000, sorry. 16,800. That's less interesting, right? It's not surprising if you picked a male and a female and you added their weights together. On average, you would expect their weight to be the sum of the averages of a male weight and a female weight. But the standard deviation does something different. So the variance here, so the variance of the two variables added together is the sum of the variances. So the variance here is 200 squared, and the variance here is 150 squared. And so then the standard deviation of the new variable X plus Z is the square root of that sum. So it's not just going to be 200 plus 150. It's going to be the square root of 200 squared plus 150 squared, which is definitely not going to be 350. It's going to be 200 squared plus 150 squared. Square root of that. I think actually I picked a perfect square, maybe. Maybe not. No, I think I did. Yeah, it's 250. What a lucky choice. All right, so the standard deviation here is definitely less than the sum of the two standard deviations, and that always happens. All right, I think that's all we've got time for today. Just a couple questions. Remind me, you guys have a midterm or no? But you do have like the end of chapter quizzes, right? Yes, obviously I've done them. So those quizzes aren't too bad. I think as long as you read the sections, I think the quizzes are pretty doable. You just had your second quiz, okay. All right, well, yeah. We have, I checkpoints the quizzes every 2 weeks for the class and anybody stuff works. And are the quizzes through the OLI thing? Is that what I've been doing, or is it different? No, okay, they're not. Okay, then I don't know what the quizzes look like. All right, I'll take where are the quizzes? Are they on Canvas? They're assignments on Canvas. Thanks, appreciate it. Let me take a look real quick just to see. I mean, you guys are, obviously you're welcome to go if you need to go. I just want to take a look and see if there's anything she's saying about this here. Assignments.
I know that she still hasn't released the, like if you click assignments and then, I don't know if you can see, but it's under quiz 2.
Yeah, I see it.
I don't know if you can open it, but we can't. It just tells us.
I'm a student as well in this class.
Oh.
I had to be a student so I could access the textbook.
Oh, got it.
Let's see, it says take the quiz. What happens if I click on take the quiz? Oh, I can take the quiz.
Oh,
Quiz
yeah.
2. Let me share my screen here.
That's what our quiz looked like.
Yeah.
Yep.
There it is. All right, I'll take a look at this just on my own and see if you guys have any questions about it. Oh, we can. So let's see. Is there that basketball question in here? Does everyone get the same quiz?
Yeah, I'm pretty sure. This is one I got, so.
Sure. Okay. Well, yeah. If you guys have any questions you want to ask about this in general, feel free to shoot me. Maybe you can you not see it anymore, Shelby?
No, we can't. It's blocked on our side since we took it.
Yeah, I imagine once you take it, you can't look at it anymore.
Yeah, she said yesterday, I believe, that she was gonna release the answers once the scores were posted.
Sure.
And I think that she just posted the scores today, so hopefully later today or tomorrow.
Well, if you want to ask me any questions about it via either discussion in Canvas or send me an email, I'm happy to try and help out with that. Now that I know where to find it.
Yeah. Okay. Thanks.
Okay. You're welcome.
Bye.
I'll see you guys later. I'll see you. You're welcome to come on Thursday, obviously, but if you don't come on Thursday, I'll see you all on Tuesday.